Okay, the normal test. Can you hear me? Okay, the normal yes. Test. Cool. Okay. First things first. As always, we're going to do Duolingo. Here we go.
V.
And the reason I do this is because loads of biology and mathematical stuff is based off of the Greek language. So
V.
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 V. Yeah.
V. Va.
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 Match the pairs. V for
V.
Z for Z,
Se. Va.
Va for va, Na for na,
Va.
Ria ria.
Ria. Va.
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 Can see what's behind me then. It's water. I think it's like
Είναι.
nero. Cool.
Ναι, το avocado.
Ne to avocado. Ne is yes, the avocado. It's water. Ine, which I can't quite remember how to do. Let's see. Ine, it'll probably be that. Nice, got it right. It's water and carrot. Interesting sentence. The avocado. Ooh, need English back. The avocado.
Το ροζ βάζο.
To rose vaso. So it's to rose vaso. Ah, to rose vaso. The pink vase.
Ναι,
Vase.
το ροζ βάζο. Ναι, το ροζ βάζο.
Ne. Ah, ne. To rose vaso. Yes, the pink vase. Cool. Hole in one. Nice, 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 nice. Sure, let's do that. Ooh, celebratory. Okay, that's that. We were doing a bit of coding last time. Basically just to make things a little bit more interesting. And I was coming up with some ideas earlier about the first kind of goals of the AI that I'm going to have to write. And I suppose in the first goals should be something like if I give the computer I mean maybe this should be a few lines down. Maybe we'll start off with just the image recognition and recognizing silly things like numbers as the tutorial does, but moving down the line, something like providing a sequence of DNA, providing a DNA sequence, and then finding, I know, some kind of position where CRISPR can be applied, something like that. So we'll see how it grows and see how it matures over time. But back to the coding, I guess. I think I left off with kind of refactoring everything a little bit, so that there was these nice little functions that were in line with the sections of the tutorial. So we'll go back into the tutorial and see how we go. New window, please. Not that I can remember much. I think maybe I output something. Yeah, this must be the. So I think I did the end, maybe the end of quick start. Yeah, predicted that. Okay, so let's just run this again. What do we get out? Ankle boot, actual ankle boot. So I predicted an ankle boot and an actual was ankle boot. Okay, that's interesting. And that doesn't change, right? Okay. I'll have to remind myself of how this works. So go to my main, go and new up a machine learning example. Okay, there it is. And then we go and run the setup, and the setup does, how do I collapse all these? Edit, view. Let me just find that out. One sec. Collapse code in PyCharm. To fold or unfold a code fragment, press Control plus numpad. Control Shift numpad minus or Control Shift numpad plus. Okay. Control Shift numpad minus. Okay, that's better. Right, so yeah, the setup function runs and it says set CUDA state, and that's just saying if CUDA is available, print it out. So it doesn't actually do anything. Okay, and then we go and new up. No, we go and run download data. Let's do that, and then that news up an example data, and so example data looks like that. Okay. Oh, how do I go back? I don't know. And then we go and excuse me, data sets, where was that newed up? That must be from here somewhere. Okay, so Torch comes with the datasets function or object, and on there's a method. We pass in this stuff, and this is download training data from open datasets for fashion. Okay, what are the ones we got here? Interesting. And then download test data from open datasets. Okay, and then we'll return that data from this method. So download data is returning the example data, and that's stored here. And then we've got the data loader. Got the data loader. And that is going to get returned from the setup loader. So let's see that. So data loader gets something from download data. No, sorry. Ha. Setup loader. That's right. Yeah. And then it passes pointers into the the data that I've prepared, and then runs this. Let's see what that is. That is a thing from PyCharm. Okay. So train data loader, test data loader goes and gets stuff. Okay. And then what happens then? Okay, and then the run function is called. So this is ended. So now we've got all the data prepared. We go and new up a so if there is something stored in this file path, model.path, which I guess there is, There it is, model.path. Let's see what's actually in there. File model.path is not associated with any, that's fine, text. So that's what that looks like. It's pretty chunky as well. Okay. So if there is something in there, load it, model equals loading models. Example neural network, save model path, okay, yep. Load state dictionary, that's going to be a Python thing, yep. Okay, and then if it's not already there, then it runs this, and it will go generate all that training data and stuff. And then, oh, we just disable those 1 second. One second. Wrong one. This one. I never know how to quit this bloody program. Right, I think that's it. Okie dokie. So, yeah, so then we go and make it basically. Optimizing model parameters, let's kind of look at that one. So cross entropy loss, that's something I learned in Manolis Kellis's video, but I can't quite remember it. Let's have a read of it. This criterion combines log softmatch and NLL loss in one single class. It is useful when training a classification problem with C classes. If provided, the optional argument weight should be a one-dimensional tensor assigning weight to each of the classes. This is particularly useful when you have an unbalanced training set. The input is expected to contain raw and normalized scores for each class. Input has to be a tensor of size either minibatch C or minibatch C d1, d2 to dk, with k being greater than or equal to 1 for the k-dimensional case described later. This criterion expects a class index in the range 0C to 1 as a target for each. This is quite, okay, let's try and read this. Target for each value of a one-dimensional tensor of size minibatch. If ignore index is specified, this criterion also accepts this class index. This index may not necessarily be in the class range. The loss can be described as loss as the function of x and class is equal to the negative of the log. Flawed expression. Flawed is the output of the expression. Oh, exponential, sorry. Haha. Yes, exponential. X taking class and putting that in. X as a function. Log of lowercase. Log of flawed exponent divided by the sum from j. Yeah. And as j keeps going, in the exponent we're putting x, whatever this array part is. This is all flawed, and that's going to be equal to negative x, whatever class was, plus log. It's too much for me to handle there. It's good though to know that this detail is here. It's a little bit over my head at the moment, unfortunately. Mainly because log. Because I haven't really learned much about log. Okay, cool. So it does this thing. this is our loss function, that makes sense. And then torch optimizer SGD, wonder what this means. See if that's a type ahead. Implement stochastic gradient descent. Okay, that makes sense. Cool. And then the parameters of our model pass in. I wonder what this is for. What's this signature here? Second parameter. LR is learning rate is 1 to the 10 minus 3. 1 times 10 to the power of minus 3. Okay, cool, whatever. And then these are local functions, okay. Run the above functionality that's been prepared. So for each one, train for the grouping. So every 5 it's going to run this method. It's going to pass in our training data with our model and our loss function. Training does... Oh, well, we did a lot last time. Gosh, this is all copied from another place. It goes through and it says... Oh yeah, this was that funny... tuple operation. Okay, compute prediction errors. There's a lot of stuff here I don't think I know enough about yet. Then it goes through this one, which is, let's see, much the same kind of detail stuff. Optimizing, and then what does it do? It saves the model. So once it's generated, it saves the model into that file path there, which I need to change over. So I'll do that. Okay, and then this prediction, and then at the end of it all, go and predict against our model. So here's our classes. So it says evaluate the model, then store into this 0, 0 test data and 0, 1. So I wonder if I wonder what this actually does though. So let me stop here. Okay. So X is filled with what? X is a tensor. And what is self.data? Self.data is an object, example data object, with test data, and test data has a bunch of classes in it. Tensors associated with it, I guess. Okay. So what is 0, 0, 0 would be, I wonder how this works in Python. Like, which array does it choose? One would imagine it's data, but then it does this. So if I were to look back in this, what has it got again? It's got this tensor. If you can't see this, neither can I. This is so small. How do I zoom in? Must be a way of, I'm trying to like zoom in with my mouse and control, but it's obviously not working. Shame. Sorry, I don't think you can see that. It's a real shame. I'm essentially just trying to study what's happening in this this array thing here, because it's not obvious to me as a noob at AI and tensors. What is that? What is the relevance of that? X data, test data should be in here somewhere. No, hang on, I'm being an idiot. Right, let's try this again. Self. Yeah, that's right. Okay, so self data, test data, and the zeroth test data is an object. It is this kind of object. Oh, I haven't even typed it. So this is the problem with no typing. Let me just try and add a type to here, because I think that will help me out a bit. Test data is filled with a fashion mnist. Let's go to that. Import that. Ooh, that's not right. Data sets, let's do that there. God, where was I? Data, that's the one. Okay. And the training data was what? This as well. Cool. So now if I go back to this code, in my predict, yeah, okay, that's cool. That's better. Let me rerun this. So self.data.testData, self data.testData is equal to that. But what about the zeroth? So it's a tensor of 10,000. Okay. Anyone able to help me here? No. Haha. Never is. We're all alone. Okay. How do these arrays work? Fashion mnist. I wonder if the fashion mnist has some special operator on it. Maybe Python allows for that kind of thing. Let's try that. Let's see. It's a dataset. Okay, that makes sense. Transform, target transform. Root directory of dataset where exist. If true, create blah blah blah. Resources, classes. So that's all that is. Is there anything from that? Let's see this. Mirrors resources, training file, test file, classes. Okay. Don't see any iterators there. Vision dataset. Initialize, get item. So these things probably mean something very important. Because that, oh no, it keeps going, dataset. thought it was the last one. Generic. This is interesting now. All datasets that represent a map from keys. All datasets that represent a map from keys to data samples should subclass it. All subclasses should overwrite meth get item. Let's see what. So this typing. Yeah, okay. I don't feel like a iterable dataset. No, that's a different thing. Get item. Don't feel like I learned a lot from that little tunnel, which is a shame. I really want to know what this is referring to. Because if I keep going down in data, it just keeps going and going and going. I'm supposing these are exactly the same structure all the way down. Yeah, there's nothing changing here. It's very interesting, actually. That is very interesting. Okay. Think, James, think. Shape. Okay, well, I will at some point need to understand this because I'm actually feeling like even though this outputs something, I don't know how. I mean, it's not like I can just, if I go here, so I've got ankle boot predicted, but what if I didn't want to predict the ankle boot? You know, so, I mean, maybe I can do something like that. What is this output? This will break now. Oh, it is that, okay. So I predicted a pullover, but actually got an ankle boot. But I don't understand how this really works yet. This is a prediction though. Okay. So I'm predicting what should happen with those two results, I wonder. Okay. What does it say? The process for loading a model includes recreating the model structure and loading the state dictionary into it. This model can now be used to make predictions. Okay. Tensors. Tensors are a specialized data structure that are very similar to arrays and matrices. In PyTorch, we use tensors to encode the inputs and outputs of a model, as well as the model's parameters. It's funny, I just spent all that time, it looks like it's going to tell me now. Tensors are similar to Numpy's ND arrays. That doesn't help me. Except that tensors can run on GPUs or other hardware accelerators. In fact, tensors and NumPy arrays can often share the same underlying memory. Eliminating the need to copy data. See bridge with NumPy. Tensors are also optimized for automatic differentiation. We'll see more about that later in the AutoGrad section. If you're familiar with ND arrays, you'll be right at home with the Tensor API. If not, follow along. Right, let's read where this is going. I see, okay. Got them over here. So these are the dependencies for this. Let's see, let's make a new function. I'm just going to call it A for now because I don't quite know what it's going to have in it. Let's grab those, copy those. Paste those in. And then tensors can be initialized in various ways. Take a look at the following examples. Directly from data. Tensors can be created directly from data. The data type is automatically inferred. Data is equal to a multidimensional array of integers. X data equals torch.tensor of that data. I think I'll put these side by side actually. Let's see how you can see. You can roughly see. Okay. From a Numpy array, tensors can be created from Numpy arrays, and vice versa. See bridge with Numpy. Okay, Numpy array. Oh, excuse me. From another tensor, the new tensor retains the properties, shape, data type of the argument tensor, unless explicitly overridden. x1's equals torch.1's like x data retains the properties of x data. Print 1's tensor xrand equals torch.rand like x data d type equals torch.float. Overrides data type of x data. Okay, let's try that. Excuse me. One's tensor, random tensor. So a tensor is tensor just a multi-dimensional array? Tensor, mathematics. Let's have a look. In mathematics, a tensor is an algebraic object that describes a multilinear relationship between sets of algebraic objects related to a vector space. In mathematics, a tensor is an algebraic object that describes a multilinear relationship between sets of algebraic objects In mathematics, a tensor is an algebraic object that describes a multilinear relationship between sets of algebraic objects related to a vector space. Objects that tensors may map between include vectors and scalars and even other tensors. My first impression from that is that there is a relationship between this and this. Let's just see what tensor AI definition is. A tensor is a generalization of vectors and matrices and is easily understood as a multidimensional array. In the general case, an array of numbers arranged on a regular grid with a variable number of axes is known as a tensor. In the general case, an array of numbers arranged on a regular grid with a variable number of axes is known as a tensor. A vector is a one-dimensional or first-order tensor, and a matrix is a two-dimensional or second-order tensor. Tensor notation is much like matrix notation, with a capital letter representing a tensor and lowercase letters with subscript integers representing scalar values within the tensor. Okay, fine, fair enough. So these are going to print. I need to run this. So this is called Tensors. Let's do another function here, def run 2 or run tensors. And we'll get rid of this. And we'll go back to our main. And we're just gonna comment that out, plop this one in there. Okie dokie. Right, run that, see what happens. I'm guessing it should just output these. And it does. Not that you'd be able to see it. Oh, I can zoom in, that's cool, okay. So there it is, exactly what it says here. Obviously randomization, because this function is randomizing. So here's our data. We convert it to a tensor. Torch.one's like, what does this do? Oh gosh, no documentation. Great. Torch.one's like. Well, okay, fine. Well, let's continue. It's good to see it's working. Attributes of a tensor. Tensor attributes describe their shape, data type, and the device on which they are stored. Tensor is equal to a random number between 3 and 4, I guess. Shape of tensor. Let's see what this does. I know. Let's do this second one. Oh gosh. And let's get these up here. Like so. Cool. So this one is going to set a tensor equal to some random thing from Torch. I don't know what that is though. If we go through it, doesn't give us any. Okay. Can we just run that? I wonder. I don't think this is going to work. It does. Torch.size 3 to 4. Data type of tensor is float32. And device tensor is stored on CPU. Operations on tensors. Over 100 tensor operations including arithmetic, linear algebra, matrix manipulation, transposing, I've lost myself, transposing, indexing, slicing, sampling, and more are comprehensively described here. That sounds good. Oh shit, yeah, wow. Okay, cool. Big old library. Each of these operations can be run on the GPU at typically higher speeds than on a CPU. If you're using Colab, allocate a GPU by going to Runtime, changing runtime type and GPU. Okay, we're not. By default, tensors are created on the CPU. We need to explicitly move tensors to the GPU using .2. So on this function here, on this method here, tensors are created. So we've got a tensor. So there should be a 2 function. There is. And the arguments is what? Args memory format. Torch. So this is. Wait. What's a star mean? Python star parameter. Python args and quarks. In this article we will learn about Python args and quarks, their uses and functions with examples. In program we define a function to make a reusable code that performs similar operation. To perform that operation blah blah blah. Yep. When we run the above, okay. In Python we pass a variable number of arguments to a function using special symbols. There are 2 special symbols. Non-keyword arguments and keyword arguments. We use as an argument when we are unsure about the number of arguments to pass in the function. Okay, fine. As in the above example, we are not sure about the number of arguments that can be passed to a function. Python has args, which allows us to pass the variable number of non-keyword arguments to function. In the function we should use an asterisk before the parameter name to pass variable length arguments. The arguments are passed as a tuple, and these passed arguments make tuple inside the function with same name as the parameter excluding asterisks. Okay. Python passes variable length non-keyword arguments to function using args, but we cannot use this to pass keyword argument. For this problem, Python has got a solution called KWArgs, keyword args. It allows us to pass a variable length of keyword arguments to the function. In the function, we use the double asterisk before the parameter name to denote this type of argument. The arguments are passed as a dictionary, and these arguments make a dictionary inside function with the same as the parameter excluding double asterisks. Here? So here's data, print the type of data for each tuple format. So intro, oh I see, you're naming them. Named variables, I see, okay. We have a function intro, we pass 2 dictionaries with variable argument length. We have, okay, fine. So in this case, function 2 can take device. So let's see if that's so. Device equal, oh yeah, look at that. Alright. And what does device take? CUDA. Let's see, device none. What? Go away. It returns a tensor with the specified attribute device. Device equals CPU. Device CUDA 0. CUDA colon 0. Okay, let's try that. On the CPU still. Okay, so what does it say? Where are we? Default, yeah, okay, so 2 method. After checking for GPU availability. Keep in mind that copying large tensors across devices can be expensive in terms of time and memory. We move our tensor to GPU if available. If torch CUDA is available, tensor equals CUDA. That's funny. How is that going to work then? No. No. Okay. Try out some of the operations on the list if you're familiar with. So I know that, yeah, CUDA is available. So do I need to set CUDA state? There's nothing to actually set up, so. Oh, I need to redeclare it. I see. Like that. There it is. Okay. Try out some of the operations from the list. If you're familiar with the Numpy API, you'll find Tensor API a breeze to use. Uh-oh, I'm not. Let's try this out then. Who can comment this out? First row. So it's a tensor of 4 by 4. 4, 1, 2, 3, 4 by 4. Makes sense. The first row, tensor 0. The first column, tensor. I don't know what that means. 0. What does this mean? And what do 3 dots mean? Oh my god. Python as array element. Colon by itself means fetch everything. A colon on the right side of an index means everything after the specified index. A colon on the left side of an index means everything before but not including. Vectorized operations with Numpy. Numpy is a numerical library designed to make working with numbers easier than it would be otherwise. For example, so we had a list of 1,000 numbers. There's no way to do vector maths without iterating through all the elements. There's a list. Copy, because you don't want to alter the original list. Print it out. For ID x in the range of 10,000, new values in the current one plus or equal 10, print 0, 1, 2, 3, 4, all up to 5, and this one, oh I see, so, okay, so it's tensor, but that has nothing after it, so, see anything else? Aha, okay. Working with multiple dimensions. Sometimes you'll encounter a data set with multiple dimensions and will need to be able to retrieve elements from it as such. In this case, we must index using multiple indices separated by a comma. To grab the first element, we would use 0, 0. The first index corresponds to rows, the second corresponds to columns, and the third to the next dimension. So the output of this one is 0 to I see. I'm not sure what this means. Range of 0 to 40. 0 to, wait, let's try it again. So sometimes you'll encounter a dataset with multiple dimensions and will need to be able to retrieve elements from it as such. mp.arrange 0 to 4, the sequence of numbers from 0 to 39. Reshape so it has 5 rows and 8 columns. Oh, that's beautiful. That's so beautiful. What a lovely function. I see, okay. In this case we must index using multiple indices separated by a comma. Understood? To grab the first element we use 0, 0. Okay. So it's interesting that, because in like C# you would do 0, close the bracket, 0 again. Very interesting. And now I understand how this works then. So the first index corresponds to rows, the second corresponds to columns, and the third to the next dimension. Okay. So going back to this one, the dot dot dot, what does dot 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 mean? Python ellipsis. Let's do ellipsis. There we go. Gives access to a specified range of arrays elements. Syntax. Return value the same as selected. Huh? The same as selected. How does that make any sense? Gives access to a specified range of arrays elements. Array, a comma, dot dot dot, comma, return value, the same as selected. Okay. Time complexity to do. Okay, interesting. Ellipsis is used for slicing multi-dimensional Numpy arrays. Ellipsis syntax may be used to indicate selecting in full any remaining unspecified dimensions. Okay, kind of makes sense. Yeah, let's see that run already. Okay, that makes some sense. Okay. Joining tensors, you can use torch.cat to concatenate a sequence of tensors along a given dimension. See also torch.stack, another tensor joining a op that is subtly different from torch.cat. Let's do that. Oops. Tensor. So tensor equals torch.ones from 2 to 2. And then I concatenate those. And what do we get? Huh, it's interesting. What are we getting? Wait, what? It's a bit hard for me to see this. So this is creating a tensor dot. I wonder if the dot means anything special here. Maybe it just tries to say it's a float. Torch.ones. T1 equals torch.concatenate the tensor 3 times into the array. That means you've got an array of 1 3 times. So now let's say I've got an array of 2. what I would have is I'd have 1 1 comma 1 1 comma 1 1, and then down 2 rows 1 1 comma 1 1 comma 1 1, and down 2 rows. Okay, fine, nice. You can use torch.cat to concatenate a sequence. Tensors, yeah. Arithmetic operations. This computes the matrix multiplication between two tensors. y1. This computes the matrix multiplication between two tensors. y1, y2, y3 will have the same value. y1 is equal to tensor at tensor 2. y2 will equal the tensor dot map matrix multiplication. Oh man, I'm so tired. This is annoying. There's quite a lot left, isn't there? I feel like it's a bad idea to stop here. I should at least get to the end and then start again if I've lost it. So this computes the matrix multiplication between two tensors, y1, y2, y3, will have the same value. So I don't know what that is. Let's just go with it. So y1, y2, y3, torch.matrix multiplication between two tensors. Let's try it. We need a tensor again. Let me do the self-contained. Let's do that. Oh, interesting. I didn't output anything. What does this return? Returns a tensor. Do that. So we get the result and then we print it out. And let's try the second one. res2, and we'll print that one out. Alright, cool. So this computes the element y's product. So what are we actually doing here? Y3 equals random like tensor T tensor matrix multiplication these aren't used, so I need to just print these out first. Let's do this. Whoops. Y1 Y2 Y1 Y2 and then Y3 and then the result. Yeah. And I guess we'll do the same with these dudes here. Z1, Z2, Z3, res2. what do we got? Machine learning run tensor 2, line 89, can only concatenate string, not tensor to string. Right, so if I were to delete this, like so, does that now work? Interesting, okay. That's because I need to have string here. Let's try that now. Okay. So y1 tensor, I wonder what the at symbol is then. Python at symbol. An at symbol at the beginning of a line is used for class, function, and method decorators. If you see an at symbol in the middle of a line, that's a different thing. Matrix multiplication. See answer showing. Yeah. In Python, you can overload at as an operator. It is named as matrix multiplication. Oh, I see. They're all the same. I see. Okay. So this is the same as that is the same as. How is that the same as that? Rand-like. Turns a tensor the same size as input that is filled with random numbers from a uniform distribution of the interval. That's interesting. So this computes the matrix multiplication between two tensors, y1, 2, and 3. y3 will have the same value. Okay, well I get the gist. And also they're doing multiply as well here and multiplies. There's so many different ways of doing it. Fair enough, that seems fine. Single element tensors. If you have one element tensor, for example by aggregating all values of a tensor into one value, you can convert it to a Python numerical value using item. So at the aggregate of the sum of all tensors, converting Python numerical value. Okay, it's interesting. So let's do that. Oops. Okie dokie. (16) class float. So if you have one element tensor, for example by aggregating all values of a tensor into one value, you can convert it to a Python numerical value using that. Where tensor is equal to one DOUT multiple dimensional array, where we aggregate the sum of them, and then we get the item and then print it out, and then print out the type. So we print it out, and the value is going to be 16, because the sum of, 4 times 4, okay. So that's going to be 25, right? Just double check this. Yeah, okay, because it's just adding them together. Awesome. That's okay, that's really cool. I see. These are lovely methods. and then this is outputting that number. So what does outputting just this do? Oh, okay, it outputs a tensor, whereas item actually gives you the value inside that tensor. Okay, awesome. Oh, that makes a lot of sense. And it also tells us that the result is a float. I see. In place operations, operations that store the result into the operand are called in place. They are denoted by an underscore suffix. For example, x.copy underscore y, x.t underscore open brackets will change x. Let's try that. Oops. So let's have a tensor of random like, and we'll make it a 3x3. So we're going to print out the tensor. We should have blah blah blah, and then we're going to add operations that store the result into the operand are called in place. They're denoted by a suffix. For example, x.copy tensor.add. Is that add? I'm not sure. I can't understand that yet. Okay, let's see what happens. One positional argument, but two are given. Oh, whoops. And like, put what star is. Jesus Christ. Python star in parameter. The script is using to define a variable number of arguments. Oh yeah, that's okay. I remember now. Ironic that I've given it some. Let's try just that then. I guess this needs a tensor. It does. So let's just do ones instead. 3x3 filled up with ones. That prints that, and then add 5 is going to equal 6. Makes sense. It's interesting, like, what is the difference between add? So if oh, I see. I see. If I do this, that's going to do 6. But I can do it inline by just doing underscore. So it's like taking a reference to the integer instead. Very cool. I like it. Very, very cool. In place operations save some memory. Oh, they save memory. Make it problematic when computing derivatives because of an immediate loss of history. Hence their use is discouraged. Yeah. Okay. Yeah. Yeah, okay. Bridge with Numpy. Tensors, how far we got? Okay. Tensors on the CPU and Numpy arrays can share their underlying memory locations, and changing one will change the other. Tensor to Numpy array. Oh, I really like that. That's really cool. What a great little functionality there. T equals torch 1, so it's a one-dimensional 5 matrix as a tensor. Prints it, so it should have 1 1 1 1 1 1 1 1 1 1, and then Numpy can share the underlying memory locations, and changing one will change the other. So I do that, and then print it. A change in the tensor reflects the numpy array. T.add. One okay, I see. So as you change it, it should update them both. Okay, let's try that. And to do that, T modded. Yeah, nice. Whereas if I did not do that, I'm guessing that that is not shared. Oh, my bad. If I do n dot n modded. Try that. So in this case, I added it with the reference, but this is saying that if I do numpy, what is the difference? So t is 1, n is 1, I modify t, I print it out is 2, and then n is also modified because they are related to each other, right? And this is, I'm assuming, a copy, but I don't think it works like that because it's still coming out as 2's. What is the difference? One is without the tensor. So we've taken out the array. Tensor array can share their underlying memory locations. Changing one will change the other. Change the tensor reflects the numpy array. Okay. Numpy array's tensor. np.ones. np. Array the tensor. Changes in the numpy array reflects in the tensor. Let's try that. I don't quite understand this one. This has been very unbiological, this so far. I think it will be a little bit like this for a while actually, because I've got a bit of mathematics to figure out here, haven't I? And then I need to get a better picture of what I actually want to achieve with this. This is the kind of thing I imagined I'd have to be doing, so it's a good thing. I think I should also dip my toes back into the chemistry part soon as well, otherwise I'll forget it. A little revision. Yeah, okay. That's what I'll do. So I think I'll probably do 2 more of these, because I'm actually finding them quite interesting. See if I can come up with some kind of project to do, and then I'll flick back over to the chemistry stuff, the chemistry formulas, and then I think I'm gonna have to unite them in some shape or form. And I think things will start getting quite interesting then. Now I have this idea of trying to do some experiments as well with DNA. So I'd like to try and work towards that goal by planning things with the AI and formula expressions. And then executing them with some kind of experiment. We'll figure out. Okay, so let's see what this does. So this is creating a lovely array for us, a little tensor. So if I do print n, will give us 5 ones. And then from numpy, changes in the numpy array reflects in the tensor. Let's see what that says then. Oh, that's interesting as well, because they managed to print out tensors just by doing that, so maybe I should try that. Something like f cool. Okay, I didn't know you could do that. And I guess if you take away the F, it doesn't work. Cool. Format. Makes sense. N. And then T. TT. Okay. What we got, what you got, what you got. N. There's an array converted to a tensor by just doing from Numpy. Fair enough, okay. Total running time of the script. No, okay. Well, that was awesome. I have to say, I really enjoyed that. Oh wow, yeah, okay, it really goes into it. Yeah. Alright, cool. For another day. For another day, that was really, really cool. Let me just push this up to Git. So I don't lose it. So I'll do Git status. Should have main. Don't think I need these. Model PyCache of data machine. Oh yeah, okay, I see. Because it has to compile them. So those are okay. So if we go and add them all now, then we go and do a little commit message saying got to data tutorial.html, learnt about tensors and manipulation of tensors, and we'll push that up. Alright, sweet. Nice. Okay, cool. That was awesome, and I shall bid you all farewell. Thanks for watching if you do, and